Alright, so this is where we left off in the last video. Sorry, I can only do 15 minutes at a time. That's all I'm allowed on this screencast-o-matic that I'm using. So anyways, we left off at exponential growth. We were talking about the conditions that are necessary for a population to grow exponentially. So what we need is you have to have enough space, you have to have enough food, you have to have very few or no predators, and you have to have lack of disease. And again, we talked about how we don't, you occasionally hear of maybe a human being eaten by a shark or some crazy incident like that, but in general, we're not hunted. There aren't human predators, there's no predators to humans. And we've gotten really good at curing diseases. Not all of them, but enough of them that we have seen our growth rate grow, our population grow exponentially. All right, so here's what an exponential growth curve looks like. We see it increasing rapidly. See that line going up? It increases rapidly. And the larger the population gets, the faster it grows. Let's think of a family of rabbits. You start with 2 rabbits. They fall in love. They have a bunch of babies. And let's say they have 10 babies. Well, then those 10 babies now have the ability to have 10 babies. And then all of those babies, now we're up to 100. Now we have 10 more babies, and pretty soon it just explodes. So the more individuals that have the ability to have babies, which the larger a population, then the faster it's going to grow. So it just kind of keeps compounding and compounding, and we see this growth curve where it just kind of starts to go straight up, it seems. So the example that's often used in science is bacteria. Bacterium is singular for bacteria. So let's say we start with, and here's a little picture of a bunch of bacteria. Let's say we start with a single bacterium, and they're going to say that it can multiply every 20 minutes. So it divides into 2 cells every 20 minutes. You guys remember how bacteria divide? Do you remember what we call that? We call that binary fission. Or if you start with 1 bacteria, it just kind of divides in half and splits into 2. So anyway, so it's doing this every 2 minutes. So at the end of the first 20 minutes, we'd have 2 bacteria. And at the end of 40 minutes, 4 cells would have been produced. And then by the end of the first hour, so now we've got 60 minutes, we'd have 8 cells. This growth doesn't seem too impressive at first, but here's where it starts to get crazy. If the number of cells doubles every 20 minutes, at the end of 1 day, this is how many cells you would have. That's how many bacteria you'd have. That is crazy. So we started out kind of growing, normal rate. Then all of a sudden it just starts to take off, and it goes straight up. And we call that exponential growth. So here's a little closer look at this. It occurs when members of a population, they're increasing at a constant rate. Very fast, but constant rate. At first, the population seems to be growing slowly. So if I could, I would cover up right here. Cover this piece up for a minute, and you would just look right here. If you just concentrate right there, it's not growing all that fast right there. So it starts out growing slowly. But then, as the population gets bigger and you have more individuals that are able to multiply, then all of a sudden it starts to just take off in a straight up direction. So under ideal conditions, with unlimited resources, you have enough space, you have enough food, not very many predators, lack of disease, you're going to see this kind of growth out of any kind of population. And it doesn't just have to, it can be humans. Even for a short while, you can see this with large mammals. You can see this happen in a whale population, potentially. It doesn't matter what organism. If you have the right conditions, that population can grow exponentially. So if you look at this curve, what does it look like to you? Let's go back to kindergarten or preschool. Come down, hook over, it looks like a J. So they actually call it a J-curve. So the J-curve is exponential growth. In reality, though, populations can't sustain this kind of growth. It'll happen for a little bit, but realistically, every organism is going to reach a maximum, right? We have a special name for that maximum. So what this is supposed to say is resources will become scarce, and waste is going to accumulate, and then you're going to see limiting growth. So that says resources will become scarce, wastes will accumulate, limiting growth. You wouldn't think of waste accumulating as inhibiting maybe a population growth, but it can definitely do that. And all kinds of organisms, I mean, if you think of the bacteria, if they're all just in one little petri dish, well, if you remember, we learned that all cells have to do cellular respiration, even bacteria. And there are waste products from cellular respiration. So even bacteria have waste products. Maybe not quite as foul as ours, but we have them, or they have them, and they'd have to live in them. And eventually that's going to be a toxic situation for any organism if they have to live in their waste materials. Because the reason our body gets rid of it is, they do that for a reason. Our body doesn't want that. That's not good for us. Can you imagine if we had to live in our waste material? And I think back to times like, and even maybe Miss Core can share with you things about history of man, but when I went to France, we didn't have Spanish in high school. We had French instead, and we went to France. And when we first went there, they told us the Seine River is the river that goes through Paris. And, Paris has been a very, very, very heavily populated city for, hundreds and hundreds of years. And it was for a very long time, that was where people just went to dump everything that they didn't know what else to do with. So it was kind of just this source of dumping. And you can imagine how gross and filthy that river was. And even when I went to high school, granted that was a while ago, they said people weren't allowed to even go into the river at all because it was so toxic at that time. So even humans, we've gotten better. We've learned that we can't live amongst our waste material. So in addition, competition also. We're going to end up competing for resources. So you might run out, resources are going to become scarce, you might be living in your waste materials, but also you're going to be competing now with a lot more individuals. And so that's going to intensify as the population grows. And so at the top of all of this, we reach something called a maximum. And the maximum that any ecosystem can hold, the maximum number of individuals that any ecosystem can hold or support or feed, is called the carrying capacity. And if you think of capacity is telling us the maximum that something can hold. If you go on a bus, it says maximum capacity is, 50 people. If you go on an elevator, it says maximum capacity is 2 tons, or some number. I'm just throwing out random numbers, but that's just for examples. So our carrying capacity when we're talking about populations and ecosystems. So exponential growth cannot go on forever. Eventually we're going to reach a carrying capacity. So at first, like we said before, a population may appear to be experiencing exponential growth. But then, when resources become less available, or disease hits, or something else, that population is eventually, that growth is going to stop or slow. And then we see it kind of playing out at the top. And we call that carrying capacity. So how will resources be limited during the growth of a population? Food will become more and more scarce. There may be water shortages. You can think of a drought. A drought is going to affect so many organisms. A drought can affect a plant population. If a plant population is affected, it's going to affect maybe a population of herbivores. And if a population of herbivores is affected, it might even affect a population of carnivores. So when food becomes scarce, you can see shortages. When water becomes scarce, you can see a change in the population growth. A disease might be introduced to a population. And then the population might run out of space. That might be with the humans. That might be what our carrying capacity looks like, running out of space. Additional predators may be attracted to the rising prey population. I highly doubt that we're going to have that problem as humans, but it could happen. Let's say, though realistically in nature, when would that happen? Let's say a rabbit population went crazy. I think the coyotes might like that. You might see more coyotes moving into the area because there's enough food there for a whole bunch of them. So additional predators might be attracted to the rising prey population, and that's going to then, once the rabbit population skyrockets, well, then those coyotes come along and they kind of even it out, maybe even take it back down to a different level. So there's going to be increased competition, and then the accumulation of waste. So these are a lot of things that can affect a population growth. Food becoming more scarce, water shortages, disease, space, predators, competition, and then living amongst your waste. So those are a lot of limiting factors. So like we said, eventually every growing population is going to reach its maximum, which we call the carrying capacity of an environment. So here's your definition. Carrying capacity is the number of individuals the environment can support over a long period of time. Sometimes an environment can, for a short amount of time, it can support way more individuals than it can over a long period of time. But over a long period of time, the carrying capacity so over a long period of time, the carrying capacity is supporting a population over a long period of time. So if we look here, the darker line, the one that goes up and straight across, that's kind of what we think of when we see the carrying capacity. You can see you have exponential growth. The population is exploding, 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 but you know what? That's all that environment can hold anymore. And so then all of a sudden it planes off. And this is the maximum that it can hold. And as long as something doesn't happen to that population to make it decrease, it'll stay right there. But realistically, the line isn't usually very straight. You might have an overshoot. So like at first, it's actually supporting more than it should be able to. And then what will happen is competition or disease or something is going to kind of really take hold of that population. Then you're going to see it decline even below carrying capacity. But eventually, you know what you'll see is it kind of just stays. If we were to average it all out, it would be kind of right along that straight line. So that straight line is maybe more like an average than it is the true picture, the true depiction. So what they're looking at with this overshoot is it'll be overshooting the carrying capacity, then many are going to die and starve, and then it's going to drop below, and like I said, it's just going to eventually average out, and it'll fluctuate. But all those fluctuations are eventually going to average out, and we call that, so don't, on anything that I'm going to show to you guys, I'm going to use a straight line. I don't want to be vague. Just know that realistically in nature, nothing is ever as perfect as a straight line. There's always going to be like fluctuations and exceptions and different things. So that isn't very realistic, but that's the one that we're going to look at. Now, logistic growth kind of combines the two of them. We have exponential growth for a while. Then the